thermochemical equations. Okay, actually, say equation means equation, but what do you mean by I am great, Ralam? So now we, chemical equation means it is a brief representation of a chemical change in terms of symbols and formulae of the reactants and products. For example, we write carbon plus O2 to give CO2. So this is a chemical equation. Okay, and in case heat energy is involved, either it is absorbed or evolved, right? Then that equation where say carbon is in solid state, so state is mentioned, okay, and just say oxygen has formula O2, carbon dioxide has formula CO2 gas. So symbols of reactants and products, right, along with their states and enthalpy, how much enthalpy change is there. So such an equation is called thermochemical equation, as the name suggests. Okay, so in thermochemical equation, first of all, if exothermic reaction is there, like this is a combustion reaction, so it is delta H is negative, and for endothermic reaction delta H is positive. Okay, and the values of delta H are normally in standard state. Standard state means, what do you mean by standard state in thermodynamics? Can you tell me what do you mean by standard state in thermodynamics? If it is not mentioned, okay, that is the standard state. So in normal form, okay, in general form, what is the standard temperature and standard pressure? Don't confuse it with STP, standard temperature and pressure. So keep in mind, standard state of any substance in thermodynamics means any substance at temperature 298 Kelvin and pressure 1 atmosphere. Okay, that is standard state in thermodynamics. Okay, second thing, the coefficient of different reactants and products involved in the equation are in terms of moles. Okay, even fractions may be used, like say if we have N2 gas and H2 gas to give NH3 gas, so you can write it as 3/2, okay, half, okay, means half mole of nitrogen gas can react with 3/2 moles of hydrogen gas to give 1 mole of ammonia gas. Or we can write it as N2 gas if we multiply with 2, okay, N2 gas plus 3H2 gas to give 2 NH3 gas. So this is defined as, how do we call it, 1 mole of nitrogen gas react with 3 moles of hydrogen gas to give 2 moles of ammonia gas. Okay, and for indicating physical state of each substance in a chemical equation, G symbol is used for gas, L symbol is used for liquid, okay, and S symbol is used for solid. And if it is aqueous solution, then you write it as AQ. Okay, this is L is used for pure liquid. Okay, if there is a large excess of water in which the substance is dissolved, we write it as AQ, that is the aqueous solution. Okay, say physical state should be mentioned because in different physical states enthalpy change is different. Let us take an example, like if we have H2 gas, when it react with 1 mole of H2 react with half mole of O2 gas to give 1 mole of H2O, in liquid state, or H2 gas react with half mole of O2 gas to give 1 mole of H2O gas. See, in first case, reactants are same. 1 mole of H2 gas, 1 mole of H2 gas. Half mole of O2 gas, half mole of O2 gas. But products formed are H2O liquid and H2O gas. So energy involved are different. Like if we write it like this. See. Obviously reaction is exothermic because H2O is associated through hydrogen bonding. So enthalpy of the reactant, okay, and enthalpy of the product. Tell me, H2O liquid or H2O gas, which one has higher energy? Out of H2O liquid and H2O gas, which one has higher energy? This is enthalpy, okay? Tell me, out of H2O liquid and H2O gas, which one has higher energy? Let us say it is for H2 gas plus half O2 gas, average energy of these two. Okay? Because delta H is, what is delta H? Sum of the enthalpies of reactant, sum of the enthalpies of product minus sum of the enthalpies of reactant. Tell me, out of H2O gas and H2O liquid, which one has higher energy? Steam causes more burn than boiling water. Do you know that? You have a question in class 10th or maybe 9th, I don't know. But this is a question. That means, which one has higher energy? Obviously, gas. H2O gas has higher energy than, yes, latent heat, than H2O liquid. Okay, so that means difference in energy for H2O gas is less, means energy released is less, and in second case energy released is more. Okay, so when liquid is formed, delta H is minus 286 kilojoule, and when gas is formed, delta H is minus 242 kilojoule. Got it? So that means this part is also very, very important. Okay, we should see that in which state the product is formed. Okay, yes, any doubt up to this? Yes, beta. Now again, coefficients. If we talk in terms of coefficients, see, if we have, okay, H2 plus half O2 gas to H2O liquid, energy involved is minus 286. So if we multiply it with 2, if coefficient is multiplied by any number, with same number we have to multiply the enthalpy. So coefficients are also very important. Okay, if coefficients are multiplied or divided, then value of delta H is also treated in the same way. Or if we write it like this, see 2H2O liquid to give, or simple H2O liquid to H2 gas plus half O2 gas. See, in the forward reaction, delta H is minus 286. So in the backward reaction, delta H is plus 286 kilojoule. Okay. So these are called laws of thermochemical equations or laws of thermodynamics. So let us see rule number 1. Okay. That if we have A to B, delta H involved is let us say X kilojoule. Okay. And C to D, delta H involved is Y kilojoule. Okay. So in rule number 2, if we multiply first equation with 2, with any coefficient, okay, so delta H becomes 2x kilojoule. Okay. And if we multiply it with 3, any numbers, then delta H becomes 3 times. Okay. I think this cannot be a rule. We suppose it like, okay, suppose A to B delta H is X and C to D delta H is Y. So rule number 1 is multiplication. This is multiplication rule. Now division. Division. Let us divide A by 2. Say if we divide reactant, we have to do same for the product, and delta H behaves like the same. Okay. Now same if we have 1 by 2 C to 1 by 2 D, delta H is again Y by 2. Okay. Now third, rule number 3. A to B, delta H is X, and C to D, delta H is Y. Okay. Now we add them, means addition rule. Rule of addition. If we add these equations, same we have to do with enthalpies. Okay. Now rule 4, subtraction rule. Okay. Now in subtraction rule, what we do, if we have A plus D to B plus C, okay, that means we have written second equation in a reverse order. Okay, that is subtraction simple. So delta H becomes X minus Y kilojoule. Okay. Rule number 5, reversal rule. Means A to B, delta H is X kilojoule. So B to A, delta H becomes minus X kilojoule. Delta H becomes minus X kilojoule. Okay. Got it? So these are the rules pertaining to reversal addition, subtraction, multiplication, division. Means whatever you do with the equation, you have to perform same, means what do I say, same operation on the enthalpy. Okay, got it? Same operations. Okay, right. So now next is heat of reaction or enthalpy of reaction. So it is denoted by delta R H. Okay, delta R H. This R indicates enthalpy of reaction. So what is enthalpy of reaction? It is change in enthalpy that accompanies a chemical reaction represented by a balanced chemical equation. Okay, change in enthalpy that accompanies a chemical reaction, right? So now let us say we have a reaction, A moles of A react with B moles of B to give C moles of C and D moles of D. Okay, so enthalpy of reaction is equal to sum of the enthalpies of reactant, sorry, sum of the enthalpies of product minus sum of the enthalpies of reactants. Let us write with capital letter. So now it is equal to C into enthalpy of C, okay, plus D into enthalpy of D minus A into enthalpy of A plus B into enthalpy of B. So that's it. This is enthalpy of the reaction. Okay, that is enthalpy of product minus enthalpy of a reactant. Now factors influencing the enthalpy of reaction. So enthalpy of reaction depends upon the number of factors which we have discussed just now. First factor is physical state. Of reactants and products. Physical states of reactants and products. So best example I have quoted you, that H2 gas plus half O2 gas to give H2O liquid and H2O gas. So when it is in gaseous state, enthalpy of reaction is minus 286. When it is in the liquid state, enthalpy of reaction is minus 242 kilojoule. If you don't want to remember these values, just write that if we change the state of the reactant or product, there is a change in enthalpy. Okay, means change in physical state change the enthalpy of the reaction. Now second is quantities of reactants, but better to remember the values for the formation of H2O and CO2. Okay, so see, quantities of reactants. So you know, when we have H2 gas plus half O2 gas to give H2O liquid, enthalpy of reaction is minus 286 kilojoule. And if we double it, we multiply it by 2, then enthalpy of reaction becomes 2 times, means double. That means if we increase the quantity, the enthalpy of reaction also increases. Okay, means heat absorbed or heat evolved increases on increasing the quantity of the substance. Okay, that means if when the number of moles of the reactants are doubled, enthalpy change also becomes double. Now third is allotropic modifications of reactants. Yes, name the allotropes of carbon. On changing the allotropic form, enthalpy of reaction are different for different allotropic forms of particular substance. For example, very good, graphite and diamond, even fluorine. Okay, so they are most common. So carbon when react with O2 gas to give CO2 gas, or carbon in the form of diamond with O2 gas, it also gives CO2 gas. So if we use different allotropic forms, then enthalpy of reaction involved is different. In case of graphite, it has minus 393.5 kilojoule, and if we have diamond, then its value is 395.4 kilojoule. So tell me, which allotrope is more stable, diamond or graphite? Which is less energetic? Out of carbon and graphite, which one is more energetic? See, this is CO2 gas. Okay. Enthalpy. Okay. Now tell me, out of carbon, diamond, these values are given to you. See, these are the values. Okay. So, which one is higher energy? Diamond or diamond energy of the diamond is less. See, in case of diamond, energy released is more. That means diamond has higher energy than graphite. See the value of enthalpies. So that means diamond when converted into CO2, energy difference is more, and when graphite is converted into CO2 gas, energy released is less. So that means graphite is less energetic, or we can say yes, more stable thermodynamically. So that means thermodynamically more stable allotrope is graphite. Thermodynamically more stable allotrope is of carbon is graphite. Keep in mind. Done? Okay. Next is conditions of temperature and pressure. This is third form. Then now fourth one. Fourth is conditions of temperature and pressure. So a chemical reaction with different enthalpies at different temperatures and pressures, and values are generally expressed under standard conditions of temperature and pressure. Standard conditions are 298 Kelvin and 1 atmosphere pressure. So enthalpy of the reaction under standard conditions of temperature and pressure is called standard enthalpy of a reaction. Okay, so generally for standard case we write it like this, sometimes like this, or this is known as standard enthalpy of reaction. This is called standard enthalpy of reaction. That means when temperature is 298 Kelvin and pressure is 1 atmosphere. If we change the temperature and pressure, there is a change in enthalpy of the reaction. Done? So temperature and pressure conditions are also affecting the enthalpy of reaction. Okay. Now, fifth point is conditions of constant pressure and volume. Conditions of constant temperature and volume. So, enthalpy of the reaction is expressed at constant pressure or sometime at constant volume. In general, it is at constant pressure. Okay. So, what is the heat change at constant pressure? That is called enthalpy change of the reaction, or simply enthalpy of the reaction. And at constant volume, yes, at constant volume is called change in internal energy. Okay. And what is the relation between change in enthalpy and change in internal energy? Change in enthalpy is equal to change in internal energy plus P delta V or delta Ng RT. So conditions of constant pressure or constant volume also affect the change in enthalpy or heat, we can say, enthalpy, heat of the reaction. Okay. So these are the 5 factors. First is physical state of reactant and product. Second is quantities of the reactants. Third is allotropic modifications of reactants, conditions of temperature and pressure, or conditions of constant pressure or constant volume. Okay. So this is all about enthalpy of the reaction. And at the same time, enthalpy of reaction is sum of the enthalpies of the product minus sum of the enthalpies of the reactant, or sum of the bond enthalpies of reactant minus sum of the bond enthalpies of product. Okay. Or in different units, I will explain it in the next lecture. That is different types of enthalpies of reaction. Next lecture is going to be very, very important. Okay. Today's lecture is about thermochemical equation. So what is thermochemical equation? Any equation which involves symbols of molecular formulae or symbols of reactant and product and their coefficients. Okay. At the same time, physical state and heat change. That is called thermochemical equation. Okay. That is called thermochemical equation, which involves first symbol of each element or a molecular formula of the compounds. Second, physical state of each reactant or product. Coefficients means number of moles. Those coefficients are called number of moles. Coefficients of each reactant and product. It will take 3 more lectures, beta. And next is heat change, energy absorbed or evolved. So these are the 4 factors which are present in an equation, chemical equation, then that is called thermochemical equation. Okay, done. So that's all for the day.